Okay, so we're going to go ahead and get started. We know that we have more people that are continuing to come in. And we know a lot of people that are going to view this on video, but want to get started because we have a really great program today and we want to take full advantage of our experts' time. And so our expert is Tom Solomon. He's with 350 New Mexico. He spends a lot of time working on fossil fuel issues and advancing clean energy in New Mexico, but also I think beyond. At least I've heard him speak in a number of forums. And as soon as I heard Tom speak about hydrogen and a hydrogen hub proposal in New Mexico, I knew we needed to have him at our Voices Coalition webinar series. For those who don't know, Voices stands for Victory Over Infrastructure, Clean Energy Instead. And so Tom is going to be a great addition to our webinar series and help us understand the true facts when it comes to hydrogen and proposed hydrogen hubs. And so with that, Tom, but I want to make sure I remind people this webinar is of course being recorded. So please, if that's a concern to you, don't say anything in the chat or say anything verbally that might be worrisome for you to be on video. But also, as is our practice, we're going to ask that questions be added into the chat. So one, as they come to your mind, you can put them in the chat, and then we'll pick them up at the end of the program. Or of course, you can wait till the end of the program and put them in the chat. But that way we'll make sure that everybody remembers their questions and we're really efficient at gathering all of them to put to Tom for answering. So with that, Tom, I'm going to turn it over to you.
Thank you very much, Maya. Thank you for the invitation to speak to the group today. My name is Tom Solomon, and I am a retired electrical engineer and have been co-coordinator of 350 New Mexico for, about a decade now. And this talk is called the Blue Hydrogen Briefing, and I will share my screen now. And hopefully that is coming in live and loud and clear. The reason I put this briefing together, and you can see my opinion of blue hydrogen in the graphic there of the Hindenburg blowing up, was because it was a big issue during the last legislative session in New Mexico, where the administration made an attempt to pass nothing less than 4 separate hydrogen hub bills to advance, making hydrogen from fracked methane in the state. And so this was a briefing that I shared with many different legislators in our legislature to give them an understanding of what was coming and why it was a really bad idea for New Mexico. And so that's the context. And here we go. The key messages for blue hydrogen, which is the industry term for making hydrogen from methane, but doing some carbon capture and sequestration to try to make the carbon footprint a little bit better, not nearly good enough. The key messages of the presentation are kind of condensed here, and I will just go through them quickly. So making hydrogen from methane is a fossil fuel program, hard stop. Any subsidies for making hydrogen from methane are fossil fuel subsidies because of that. The science says that the carbon footprint of making blue hydrogen is more than 20% worse than just burning fossil natural gas directly. There are now 2 scientific studies that prove that. Hydrogen itself is a very wasteful energy carrier. It's more than 2 times worse than just using electricity directly, which makes the economics of using hydrogen pretty lousy. And that makes the electricity from making electricity from hydrogen much costlier than doing it from the cheapest sources of electricity, which are now solar and wind. And it means that it's largely unprofitable per the proposal that is active in New Mexico today. And I'll show you that. Job number 1 for the climate is to urgently build massive amounts of wind and solar and shut down the coal and gas-fired power plants that are polluting our climate, not to divert energy resources and green energy into making hydrogen. And there were 4 hydrogen hub bills in the New Mexico legislature in 2022, which were all defeated because of massive opposition that was rallied in grassroots groups and with our legislators. One key factor to remember is that there is this Orwellian term, clean hydrogen, kind of like clean coal, which really means that you can emit into the atmosphere 2 kilograms of carbon dioxide for every kilogram of hydrogen that you produce. And so that is not clean. So why is all the hydrogen hype happening, in industry and in government circles? And the reason why is that it's being really pushed by oil, gas, and pipeline companies. It is not being pushed by the environmental community. There have been several reports warning of the impacts of making hydrogen from methane. This one from Earth Justice is very good, and I will put the link to this presentation in the chat, or maybe Maya can, so that you can access all of the links in these slides and review it afterwards. But the hype is coming from oil and gas and pipeline companies. Specifically, there was a consortium generated in the European Union around 2017 called the EU Hydrogen Council, and they conveniently put their logo page on their website, and I have circled or highlighted in red outline all of the fossil fuel companies that are part of that consortium, and you can see a bunch of them there. And they include British Petroleum, Shell, Chevron, Saudi Aramco, Sinopec, ADNOC, Kogas, Petronas, SoCalGas, an international consortium of fossil fuel companies. And they're doing it because promoting the manufacture of hydrogen provides a path for them to sell more gas and to delay the clean energy transition. And behind it all is this oil and gas industry PR firm called FTI Consulting, and they created the European Union Hydrogen Council. And how do we know that? Well, the mailing address of the FTI Consulting and the EU Hydrogen Council were one and the same address in Europe when it came out. So that's where that comes from. Let's talk a little bit about hydrogen itself. It is the smallest atom in the universe. It only has 1 proton. Which means that it is extremely reactive, and essentially you don't find it in nature by itself. You find it in nature combined with other atoms like oxygen in the form of water, or combined with carbon in various hydrocarbons, most notably methane, which is CH4. And in order to create pure molecular H2, hydrogen, it takes a lot of energy to pry off those other atoms to just create pure hydrogen. And that means that hydrogen itself is really not a fuel. You don't find it in nature. It is an energy carrier because you've got to invest all of this energy into creating it in the first place, and then you physically transport it somewhere else to do its work. And that takes a lot of energy itself. So that's the basics of hydrogen. Hydrogen used today is mostly in 3 main industry segments, primarily in the production of ammonia for fertilizer, which is NH3, is the main component of a lot of fertilizers. In petroleum refining, a lot of it is used in the manufacture of diesel fuels, that's 25%, and then methanol production is all another 10%, and there's a miscellaneous additional 10% of other stuff. So that is where hydrogen is used today. And this is essentially all what's called gray hydrogen, which means that creating it emits massive amounts of carbon dioxide into the atmosphere. And the production of hydrogen in the world today is one of the major sources of global warming emissions. About 2.3% of all global warming emissions come from producing hydrogen for these various purposes. And this is a little chart that I'm going to use to explain the various ways of creating hydrogen and the colors that they've assigned to it. And I'm just going to concentrate on these left 3, the green hydrogen, gray hydrogen, and blue hydrogen. And so here we go. If you want to create green hydrogen, you'd like to start with some, non-carbon emitting source of electricity, ideally solar or wind, but some people count nuclear in that category. And then you basically take that electricity, you run it through an electrolytic cell, an electrolyzer, which is full of water and this machinery that runs electricity through it. And off of one electrode bubbles oxygen, and off of the other electrode bubbles hydrogen, and you capture the hydrogen and you call it green hydrogen because it didn't emit any carbon dioxide during its production. Well, a very tiny fraction, like 0.25% of all hydrogen produced in the world today, is of this sort. The vast majority, like 98+% of all hydrogen, is what's called gray hydrogen, which means you take natural gas, also known as methane, CH4, and you run it through a very high temperature, high pressure operation involving steam, called steam methane reforming. And this is what one of those industrial installations looks like. And out comes hydrogen plus about 9 times as much carbon dioxide as hydrogen is produced. And that gets emitted in the atmosphere. And that's why this is a major source of global warming emissions, the creation of hydrogen from natural gas. If, however, you make an attempt to capture some of that carbon dioxide, emphasis on some, in a process called carbon capture and storage, also abbreviated CCS, and you capture some of that CO2 and sequester it underground in some fashion, then you relabel that hydrogen as blue hydrogen. Less of a carbon footprint, but still has some significant carbon footprint. In 2019, over 98% of worldwide demand, which is about 76.5 million metric tons, was sourced in this gray fashion from fossil fuels. And 2020, about 0.2 million metric ton was of the green variety, which means it's about a 0.25%, 0.26%, according to SP Global. And there we go, 2.3% of all global carbon dioxide emissions come from producing hydrogen. So that is the story of the colors of hydrogen. They like to convince you that green hydrogen is what they're talking about, but it is a tiny fraction of what's produced. The vast majority is of this very carbon intensive gray kind. This is a chart that I'm going to use to demonstrate how inefficient hydrogen is to produce compared to electricity, and is a chart put together by a European Union group called Transport and Environment. And I am just going to, again, concentrate on the left 2 columns, which compares the case of using hydrogen to power a vehicle versus electricity to power a vehicle. And we've got, this left column is direct electrification. So ideally you used 100% renewable electricity. And of course the grid is not 100%, but that's the ideal case. And you do that versus using that electricity to produce hydrogen as your energy carrier to then run a fuel cell vehicle. And as we say, hydrogen is not a natural fuel. It's an energy carrier like electricity. It is less than half as efficient as electricity in carrying that energy to somewhere else. And let's just go through the 2 columns quickly. So you've got various steps that have to be used in order to transfer that electricity to the wheels of a car. And each one of those steps has some losses. So, transporting the electricity in wires, that's about 6% losses, so 94% efficient. And then you've got 5% losses each in the charging equipment, battery charging efficiency, converting AC to DC, and then the efficiency of the electric motor itself. And you multiply all of these losses together, and you've got about 77% of your original renewable electricity that's used to power the wheels of a battery electric car, which is actually very, very good compared to certainly the efficiency of a gasoline powered car. If instead you compare it to a fuel cell electric vehicle run on hydrogen, you have these additional losses. And these three steps are the most lossy. So electrolysis itself, remember that process of taking electricity, passing it through water, and then bubbling off the hydrogen, that's only about 76% efficient. And then you've got the physical transportation of hydrogen, which is a molecule, not an electron. So that is much more lossy. It's only 89% efficient. The fuel cell itself is not very good at all. It's about 54% efficient. So you lose, 46% of your electricity in the fuel cell, and then you've got the same AC to DC and engine and motor efficiencies, and all of those losses together mean you've only got 33% of the original electricity that you use to create, in this case, green hydrogen that powers the wheels. So the ratio of 33 to 77 is 2.3, and that is why we say hydrogen is a wasteful energy carrier, about 2.3% worse than just using electricity directly to power a battery electric car. And these same factors, influence the economics of many of the other applications of hydrogen in the cases that they want to use it for. And this little humorous graphic shows you what it is that industry would like to convince us hydrogen can be used for. And it's all of these various things, aviation and ferries and, coastal and river vehicles and trucks and trains and metro buses and mid-temperature industrial heat, commercial heating, all of that stuff. These red boxes show you where hydrogen is really used today. So if you take all of these uses that are actually theoretically possible to use hydrogen in, and you organize them, you get to the slide that I'm going to show you on the next page. But just like no person in their right mind would use a Swiss Army knife to build a house, you'd use a tool designed for the job, like, a power saw or an electric drill. You use the right tool for the job, and in most cases, hydrogen can't compete. So if you organize these things as Michael Liebrecht did in this nice chart and give them a grade and a ranking from A to F or G, you find, these various cases of using hydrogen, with the current uses of hydrogen really on the top row, fertilizers, methanol, and all of the various uses in fossil fuel production. Increasingly, as you go down the chart, it becomes less and less competitive with direct electrification. And so it's just dumb to use it in some of these cases on the bottom. But that's what industry would like to do. They would like to expand the use of gray hydrogen or blue hydrogen in all of these other use cases that are really not very competitive, in order to expand their market share for producing methane. And, more extraction of natural gas, more money for them to sell it, and for the pipeline operators, and that's their motivation. In New Mexico, we had a particular example of wanting to do this, and I'll go through this quickly because this is very specific to our state. But there is an old coal-fired power plant in the middle of the state, near Pruitt, New Mexico. It actually closed down in 2020 because after 40 years, producing electricity from coal really can't compete against solar and wind anymore. So they shut it down. It used to employ about 107 people there. It was a 253 megawatt coal-fired generating station. And their proposal is to convert this to a plant that both produces hydrogen and then uses that hydrogen to generate electricity. And they created a consortium called EH2, which stands for Escalante Hydrogen Power. And they originally said last July that it was going to cost $425 million. Their more recent estimates is going to be $600 million to do the conversion to produce hydrogen. and from natural gas. And the reason why it's so expensive is that they got to do a bunch of other stuff in addition to converting the plant. They have to build an air separation unit, which is a way of cryogenically freezing the atmosphere to separate out pure hydrogen, which is a required component of steam methane reforming. Then they have to build a steam methane reformer, which is, that plant. And they have to build a carbon dioxide sequestration unit to satisfy the blue part of blue hydrogen. They don't have a picture of that. But all of these things take a lot of electricity to run, which means they're parasitic loads off of what used to be, provided to the grid. So instead of, producing 253 or so megawatts to the grid, after you subtract all of these parasitic loads to run these additional operations, they maybe will get 164 megawatts out, which will mean that the plant is unprofitable. What they plan to do in addition to make it profitable is to potentially inject 5% of that hydrogen into a natural gas pipeline, which is very problematic, and to make something they call green cement, which is very problematic. It's basically, I think, using the hydrogen as a source of combustion to create the heat that is part of cement manufacturing. So this is their flow chart that talks about how they're planning to do that. And again, this is a very New Mexico specific project, so I don't want to go into too much of the details, but this is what they're planning to do. This is some of the chemistry for how a steam methane reformer works and why they need an air separation unit to create the hydrogen that's part of this formula, all of that stuff. So that is what goes into making a hydrogen generation plant create electricity from hydrogen. There is a very credible international organization out of France called Lazard Investments in Banking, and they publish every year a very good comparison of what are the levelized costs of energy for various sources of electricity generation. And this last year, they conveniently added a little box that says, if you do hydrogen blending into natural gas, what is the cost of that for creating electricity? And as you see here, they have various kinds of solar, they have geothermal electricity and wind and gas peaking plants and coal, and gas combined cycle, which is the most commonly designed kind of a gas power plant. Well, if you add 20% hydrogen blend into that gas, it basically increases the cost of electricity by 49%, from about $60 a megawatt hour to $89 per megawatt hour. So not competitive. The company that is putting up the funding for the conversion of this Escalante coal-fired power plant is called Tallgrass Energy. They have since been acquired by Blackstone, but they acquired a 75% membership interest in Escalante Hydrogen Power, according to their own website. And who is Tallgrass Energy? Well, they are an owner and operator of 8,300 miles of natural gas pipeline, in addition to some crude oil pipelines. So they're also going to use the 45Q tax credit to generate some tax benefits from doing this. So you can guess that their interest is in making sure that they have a customer for their main product, which is natural gas. There's another company in New Mexico called Biotech, which produces gray hydrogen. It's a spin-off from Sandia National Labs, and they just plain produce gray hydrogen, no attempt to capture the CO2, and it emits CO2 in a 9-to-1 ratio to hydrogen. So for every 1,000 kilograms of hydrogen they produce, they just emit into the atmosphere 9,090 kilograms of carbon dioxide, according to this chart on their website. And so, their fantasy is to create these modular hydrogen hubs, put them adjacent to an interstate highway, and have them be fueling stations for interstate fuel cell vehicles, be they cars or trucks. Germany has looked at the use of hydrogen from natural gas, and they issued a statement earlier this year, January, that said they are not going to provide subsidies for the creation of blue hydrogen because of its bad footprint, a carbon footprint. And that leads us into wanting to take a look at the science. So there have been two very credible scientific papers published, peer-reviewed, which is the gold standard, that says what is in fact the carbon footprint of producing hydrogen from methane. And the first of those is from Robert Howarth out of Cornell and Mark Jacobson out of Stanford. And the takeaway pull quote from their abstract is here in the red box. To call it zero emissions fuel is totally wrong. What we found is that it's not even a low emissions fuel either, meaning blue hydrogen. The greenhouse gas footprint of blue hydrogen is more than 20% greater than burning natural gas or coal for heat. And they did that by looking at the full life cycle emissions, including a lot of upstream fugitive emissions from producing, extracting that methane. And you add all that up and do honest accounting, and you come up with this conclusion. And I read this paper multiple times. This is kind of a key part of their assumption set, which is they're assuming about 3.5% of upstream methane emissions as a percent of consumption, which turns out to be a very generous assumption. But they modeled that leakage all the way down to 1.45%. They assumed 85% capture of the carbon during steam methane reforming, which is also reasonably generous. But most importantly, they assumed an additional 65% capture of the flue gases from the combustion of whatever it is that produced the electricity, which basically nobody also does. So they made some pretty generous assumptions. And if you process all of that information and kind of put it into a pie chart, which I did, you end up with this conclusion. So what is the life cycle emissions of creating blue hydrogen? Well, it's basically 63% of it is from upstream fugitive methane. 23% of it is the uncaptured carbon dioxide that comes out of powering the steam methane reformer. That's even after the 85% carbon capture. And then you've got some miscellaneous pieces from the incomplete capture of powering the carbon capture and sequestration equipment, et cetera, et cetera. So the lion's share of the footprint of producing hydrogen, even with all of this 85% carbon capture, is the upstream methane leakage, which they are not doing anything about. This is a New York Times story that covered that. And I'll just skip through this. This is the second paper that was from Australian National University. Very similar conclusions. It was November 2021. The authors said that making hydrogen from fossil fuels produces substantial greenhouse gas emissions that are the driver of global warming, even with carbon capture technology. This third study looked more at the economics of it and warned that the cost for blue hydrogen will prove prohibitively expensive without high carbon prices, has the risk of locking in the infrastructure and assets that are carbon intensive, and it is not possible to capture all of the emissions from steam methane reforming. So there's that. This is a chart that kind of shows you where it is that methane leaks from in the production and transmission chain. And I put this in here for a specific reason in New Mexico, which is that the state of New Mexico has actually honestly done a very good job of putting together some much more stringent rules about capturing methane emissions from the gas fields, et cetera. And they're very proud of the fact that they're now going to get 98% capture. Well, that's still 2% leakage, which means that that assumption in Howarth and Jacobson's paper is still pretty accurate because they modeled it down to much lower than that. And I'm not going to go through those details. However, shockingly, earlier this year in March, this study was published in Environmental Science and Technology looking at a very, very large study of methane leakage in the Permian Basin, which overlaps into New Mexico. A lot of it's in Texas. And they studied over 26,000 active wells during a 16-month study, 90,000 well site visits. And they found that, methane is not leaking at 3.5%. It is leaking at 9.4%, which added up to 194 metric tons per hour, which is shocking. Which means that burning Permian natural gas is potentially 3 times worse for the climate than running a coal-fired power plant. And I have not seen anything that convinces me that the sources of these methane emissions have been taken offline and solved in the state of New Mexico or in the Permian Basin. And what is this doing to the atmosphere? Well, the National Oceanic and Atmospheric Administration publishes data on the atmospheric concentrations of methane, and this is their chart going back to the 1980s, where we were running around 1,650 parts per billion. We are now about 1,950 parts per billion, and the increase is just happening continuously. And there has been published science that ties this secondary increase since 2008 to the US shale gas boom, where we began extracting more methane. And of course, a lot of it leaks into the atmosphere, and you can see that right here. And of course, methane is a very powerful, potent greenhouse gas. According to the IPCC, it accounts for about 25% of all global warming internationally. So this is a very big problem. And anything that promotes additional extraction of methane is directly responsible for increased global warming, which is just a disaster for the planet, as we see. And this is a scientific paper from Howarth and Jacobson that I just recently put into this slide deck that basically shows how they measured that. This is a list of the hydrogen hub bills that failed in the last session. I'm not going to go through here, but they were a collection of lots and lots of tax subsidies and goodies for industry. And we had as many as 200 people show up to legislative hearings, mostly over Zoom, voicing their objections. And they did not get out of committee, and we caused them to fail. However, the administration has signed both a hydrogen executive order and 2 different memorandums of understanding, one of which is this 4-state hydrogen MOU involving New Mexico, Colorado, Wyoming, and Utah, saying that they want to promote a hydrogen hub among these states. Bad plan. And I'm going to quickly wrap this up so we leave some time for Q&A, but I did this back of the envelope calculation to look at if you were going to spend the kind of money that they're talking about spending in the Escalante coal-fired power plant conversion to hydrogen, but instead use that kind of money to build, a similar kind of plant to deliver the same amount of electricity to the grid, 164 megawatts, just running some numbers. Basically, you could do it for a lot less. For $328 million, you could deliver enough solar energy plus a 4-hour battery backup system for only $328 million instead of, what is now $600 million. And this is my math. So you could generate lots and lots of profitable clean electricity with the same kind of money that they're proposing to waste on hydrogen. And just to put a pin in the futility of looking at hydrogen as a source for fuel cell vehicles, basically they have lost the race to battery electric vehicles. And you can see that by just looking at the charging infrastructure for battery vehicles, which amounts in June to 55,000 public charging stations of level 2 or level 3. versus the fueling infrastructure for hydrogen, which consists of 48 fueling stations all in California. So there is literally no place to fuel a hydrogen vehicle outside of California. If you want to take a road trip from California to Nebraska, good luck. You will have to tow your vehicle back. And so, all of these proponents that talk about, a nationwide network of hydrogen fueling stations for interstate truck transport or fuel cell vehicles conveniently skip the part where they have to build a nationwide infrastructure of hydrogen transport and fueling. So there's that. There are fuel cell vehicles. There are like 4 of them on the market. The main one is the Toyota Mirai, a very nice looking vehicle. And they sold in total among all fuel cell vehicles about 3,300 of them last year versus over 600,000 electric vehicles of the plug-in variety last year. So very much losing in the era of transportation. One of the other things that proponents of hydrogen like to tout is that is a way for decarbonizing lots of industry. And they often throw out the fact that 30% of emissions come from industry. Well, 7% of that just comes from the electricity to power industry. And if you completely decarbonize the grid, then that 7% goes away, which leaves you 23% for direct emissions from industry. Most of that is from making steel, cement, plastics, and fertilizer. And there are other better ways of decarbonizing those sectors than using hydrogen in most cases, except possibly for steel, where there is a very credible case for using green hydrogen to make steel. And we can cover that in the Q&A if you want to. Last slide. So pursuing hydrogen is really a distraction from job one, which is a massive build out of solar and wind to decarbonize the grid and to use all of that electricity to electrify all other uses of fossil fuels. And that's what we should be concentrating on instead of hydrogen. And this again is the summary, all of the points that I made up front. Hydrogen is a very wasteful energy carrier and it has a very bad carbon footprint just compared to using fossil natural gas directly. We should not be promoting hydrogen as a way to make sure that we extract more methane. Bad for the environment. So why don't I wrap it up there and stop sharing my screen, turn it over to Maya. If you want to have some Q&A, I'm all ready for you.
Fantastic. That was really superb. And everybody agrees because we're filled with kudos, Tom, for your presentation in the chat. So, but let's go right to Q&A because we have a lot of questions. So for the first one, I'm gonna actually combine 2 questions. This question is from Maple. It begins with a "thanks, Tom!" ! Great visuals to understand. So she says, how do you think us people can fight this onslaught of CCS? The industry seems to have it all planned out. And I just want to add to that my question, which I think can help with the response to this. What was your actual experience with the responses from the New Mexico administration to all of these great facts and information? You said that they keep coming back with the hydrogen hub proposal. So how do they refute, this factual information that you and others have provided? And I think that's part of the answer to how do we deal with this problem?
Okay, there's a lot there, but a very good question. I'll just tell you what our experience was in New Mexico. So, how did we refute it? We basically went right at the legislature, which is, so in order to pass any of these tax incentives and grants to industry to promote the use of hydrogen, built this presentation, educated, a couple of dozen legislators, a lot of them in the New Mexico Senate, which I think is our firewall. and prevented any of these bills from passing the legislature. So that was our success. And I have delivered this presentation, you know, more than 24 times now to multiple groups, probably 36 now. I have not had any success convincing the administration, because our governor, you know, despite the fact that she's very good on the climate in many other regards, is kind of captured by the fact that we are a petro state in New Mexico. I think the number 2 or 3 producer of fossil fuels in the country, sadly. And, you know, that means that a lot of people are beholden to that industry in the state. And so the response of the administration to our success in the legislature was to issue these executive orders and to you know, engage in memorandums of understanding with the other states trying to go after this $8 billion in federal infrastructure money for hydrogen hubs. And, you know, we can't prevent that except possibly in the courts when it gets to that point, which it hasn't, because the, you know, solicitation of bids is still ongoing and there have been no decisions made. Will we fight it in the courts? I don't know. I don't know if we'd have any success. You know, it's part of the infrastructure bill, but convincing people of the facts that it is really bad for the climate, I think, is key. Convincing people of the facts that the economics of hydrogen are just dumb compared to the alternatives. I fully expect that many of the hydrogen proposals would just fall apart in the light of economic reality, having to compete against direct electrification, which is just so much more efficient and cleaner and better, and is taken off, and in electric vehicles has got more than a 10-year lead. So, you know, it's an ongoing battle. How can we fight? You know, I think is educating the people that are the decision makers that we can get to wherever you can is important. That's one reason I made this presentation, and I contribute to push it. But there are a number of people in the administration who I believe should know better. I think many of them do know better. And you know, there's all of that money involved in it, and there is massive amounts of industry hype. And there's some resources in the backup in this slide deck that you can use to rebut a lot of those talking points. There is a very good kind of coalition, which I should go look for. A bunch of hydrogen scientists have kind of gotten together and created this group called the Hydrogen Science Coalition. And you can follow them on Twitter if you like. And I will put it in the chat. Where is it? Hydrogen Science Coalition at EH2 Coalition. And they have a website, also good. There it is. And so they are a good source of debunking a lot of the talking points that you hear from industry. But it's, you know, it is hard to fight a massively funded fossil fuel industry with talking points, and they put together lots and lots of marketing materials that just makes it sound great. And but it's all a bunch of hooey, you know. So, you know,
Top talking point. It's a bunch of hooey.
Yeah.
So, Tom, we have a question from Mary, and I want you to know Mary is one of our greatest activists against fossil fuels. So when you hear this question, she's because of how she framed it, I say that I want you to know that about Mary. She says, my one question is whether isn't it too late to think we can replace our fossil fuels with solar and wind, given their mining and energy demand in producing panels, batteries, windmill parts? So far, all the renewables are only added on top of fossil fuels, no replacement yet. Thus, shouldn't we focus on removing all subsidies and permits for new fossil fuels first?
I think we should do all of the above. I think we in the opposition have been trying to eliminate fossil fuel subsidies for decades. But boy, there's just something about free money from the government that is very hard to remove. And I got lots of slides on how much fossil fuel subsidies amount to, and we should absolutely get rid of it. And if we had the votes in the US Congress to do that, we would, but we don't. But continuing to push on that is a great way to do it. But a massive build out of solar and wind is the solution for the climate, because we have an economy that is dependent upon fossil fuel energy as it stands today. And we will not be politically successful in this clean energy transition if we just promote, if we just say we're going to stop using fossil fuels at all, which I don't think is what Mary's proposing, but a lot of people misinterpret that statement to be, the economy would come to a grinding halt and then we would just lose. So we have to build out the replacement, is my opinion. We have to build out all of the solar and wind to provide the clean energy to replace our use of fossil fuels. And I think that is the best path forward. We can absolutely do that. Professor Mark Jacobson, in his studies out of Stanford and the Solutions Project, publishes lots and lots of articles saying this is how we do it. It pays for itself over time. It just needs the upfront investment. It is the way to go. Saul Griffiths, in his book Electrify Everything and his website Electrify Everything, goes into lots of detail about how you actually replace gas appliances in the home and in industry with electricity and heat in the form of heat pumps, etc. The solutions are known and are out there. We just need to get very aggressive about pushing them before it's too late. So hopefully that's a halfway decent answer.
That's a great answer. Next question. Do you know how many, and Rachel and I both asked this, do you know how many CCUS projects actually exist at this point, and how many are proposed?
There is some material in the backup on carbon capture and sequestration. The problem with CCUS is that it just has a massive, history of failure. And hey, let me show you that. So if you go to just talk about CCUS a little bit. So one of the US's main demonstration projects for carbon capture and storage was at the Petronova plant in Houston, Texas, where the US government put in like $1 billion into trying to retrofit a carbon capture facility on this coal-fired power plant. But the thing is that it took so much electricity to run the carbon capture plant that they had to build a whole separate gas-fired power plant next to a coal-fired power plant just to run the CCUS operation, which of course made it stupidly expensive. And it ended up shutting down in 2020 after just being not able to compete. This is a chart out of Science Direct on the next page. You can see the link below with all of the canceled carbon capture and sequestration projects. I think just in the US, no, some in Alberta, Canada. So, there are lots of places where it's been attempted and it fails for various reasons. Either it's too expensive, or it doesn't meet its carbon capture goals, or it just fails mechanically in a bunch of other ways. So there's that. This is a report from IEFA, which you may know, the Institute for Energy Economics and Financial Analysis, a very good analysis of carbon capture and storage history and the history of failure on it. So Real world operating plants, I think you can go into this link and see the ones that remain. There are some, but there are not many because they just keep failing. And so you probably have to go into this link to answer that question, but that's a good place to go look.
And Tom, in your presentation, you talked about some of the other industries and the better ways to decarbonize them, and then specifically said we could talk about that during the Q&A. I know some of those other industries like plastics are of particular concern to some of the folks in our Voices Coalition. So I was just actually wondering if you could go back to that and give some of that additional detail.
Okay. So this is a slide that I put together as a result of a very good interview that Dave Roberts of Volts did with Rebecca Dell, who is an expert on this topic. And if you want to go listen to the podcast of that interview, it's at the link below. But the summary of all of that is I'll just read it here. 2/3 of the emissions from industry come from steel, cement, plastics, and fertilizer. And fossil fuel industry emissions, just FYI, are counted in the energy bucket, not an industry bucket, okay? And so there are 4 key decarbonization pathways for these 4 main sectors, right? And so one is material efficiency, meaning you just use less of whatever it is, use less plastic, use less cement, use less steel. And there are many places where you can absolutely do that because, for example, in the case of cement, we massively overuse cement versus what the architects say per their calculations of what's needed. And they do that because it's so cheap. It is cheaper to use more cement than to use the labor that would be required instead to do it right. And that is a sad fact, but that is a possibility. Carbon capture and storage does work to some degree. It's not nearly as efficient and effective as would be necessary to make blue hydrogen work. But in some cases, for example, in cement manufacturing and where is the other one? In some of steel, I think, CCS is a possible tactic. Green hydrogen is the way to decarbonize a lot of the ammonia production. And well, we should stop petrochemical refining ultimately, but that and methanol, right? So converting all of the uses of gray hydrogen today to electrolyzed water, green hydrogen. So that is a decarbonization path for that. In terms of plastics, one, we can absolutely use less plastic, and we should in anywhere we can. The amount of recycling that happens in the plastic industry is pitiful. It's like, what, 9% of all plastic that's produced is actually recycled. And there's a lot of barriers that prevent that from being higher. Like there are just so many different kinds of plastic that makes the mixing and the recycling of it very difficult. And if you change the regulations to require the uses of fewer different kinds of plastic, it would make recycling a lot easier, and that percentage would go up, and that would be a path. So, right, use less, tighten the regulations to use only a few types to make useful recycling possible. And in terms of fertilizer manufacturing, use green hydrogen for that, or this very fascinating company called Nitricity, which makes fertilizer directly from green electricity and water and air, which is very cool. So you'd have to look at that. It is a Stanford startup, and they are doing some of that. In terms of steel, which is a big one, so steel, the carbon emissions of steel come from the use of, a kind of carbon called coke, which is essentially purified coal. And in order to make steel, you have to take iron ore, which is iron oxide. You have to peel off the oxygen from the iron oxide in some way. And the way they do it today is they use a high temperature process in the presence of carbon to make carbon dioxide off of the FeO2, Fe2O3, and then you end up with a bunch of carbon emissions. There is an alternate way of making steel, which instead of pulling off the oxygen from the iron ore molecule and making CO2, is you use hydrogen in a process and you just turn it into water. So you've got iron plus H2O, and the product is water. And I actually do have a slide for that. Let's see if I can find it. I would have to do this. So yes, there is a Swedish company called Vattenfall that is piloting and in production, I think, on a green steel manufacturing plant, and I believe that is the future. So those are some of the solutions. Here it is for decarbonizing the other parts of industry that don't require a lot of these solutions, except this one where you'd use, basically you take iron ore and you pump in hydrogen, and out comes sponge iron plus water, and that is the solution. And Vattenfall is doing that. So that is maybe a little bit of a complicated answer. I want to show you this one thing, which I think you will all get a kick out of. Highly recommend it. So go to slide 96 and watch the, if you want to have a humorous education on carbon capture and storage out of Australia, watch the Honest Government ad from these people, and you will be educated and have a good laugh as well. So
that's awesome. That's awesome. So we're going to ask you one more question, Tom. I know we're a little bit over, but there's been a discussion in the chat, and just wondering if you ever speak to the importance and values of planting trees or ecological restoration as part of the solution for carbon capture.
I think a tree is the best way to capture carbon out of the atmosphere. Absolutely. So I'm all for it. It's just that it has been overhyped by the fossil fuel industry as a way to solve their problem in a way that doesn't affect their profits. And so I am always a little bit cautious about promoting it too much, because it lets them off the hook, and they need to be on the hook. But absolutely, we should not be cutting down old growth forests. We should be planting more trees. And here in New Mexico, we just had some of the largest wildfires in the United States, burned down 600,000 acres of our pine forests, which is horrible. And we need to replant them, and that will capture some of that carbon out of the atmosphere. But we are currently in a part of the cycle for global warming where we may be burning down more forests faster than we can replant them globally, and that is just a terrible thing. But yes, we should be planting more trees. Absolutely agree with that. But also, in some cases, I think we should be building more with wood, because if you build something with wood instead of plastic or steel, it is a great way to sequester carbon.
Well, all right, that's a good positive recommendation. But I lied about one more question, because PK
We got one more.
One more, and PK had asked it earlier and then clarified for me. And she just asked if you could speak to the cradle to grave aspect of renewable technologies, meaning have these industries prioritize making sure the extraction of the resources needed for the tech is sustainable, and as well are the waste products being handled sustainably. So cradle to grave.
So I absolutely agree that the creation of solar panels and wind turbines, which are the two primary green technologies, plus batteries for electric vehicles need to be done in a sustainable fashion. Absolutely can be done. And there is, you know, a whole new industry for recycling batteries that is cropping up. However, I would caution us all to be aware that this objection to green technology really is being pushed by our opponents in the fossil fuel industry in order to convince some of us that you know, solar and wind has all of these ecological problems, completely ignoring the massive ecological damage that is done from fossil fuel extraction and the climate pollution that is warming the planet. So while we should push our clean industries to do as good a job as they possibly can, let us not make that a reason to slow down. Let's go as fast as we possibly can, because the benefits of even, you know, not as green as we would like it to be, green technology is still vastly better because it displaces fossil fuel extraction, which is enormously harmful. And there is lots of data, including from Mark Jacobson, that shows that the land impact of you know, clean energy will allow us to free up a lot of the land that is currently damaged by fossil fuel extraction, not to mention what we did to the, you know, to the Gulf with the Deep Horizon catastrophe that destroyed a lot of marine life in the oceans, and on and on and on. So let's do both. Let's go as fast as we can, but let's make sure that those green technologies are as sustainable as they can. And in fact, there's a lot of data that says that it takes, for example, something on the order of a year or less of green energy production from solar and wind to account for all of the electricity and energy that was required to create those products in the first place. So the carbon footprint of producing a solar panel or a wind turbine, you know, is covered by its first year of use, depending upon, plus or minus a few months, depending upon where you do it.
That's fantastic answer. Thank you, Tom. And just to let everybody know, Delaware Riverkeeper Network has a fact sheet that we did a little bit back, sort of debunking some of these arguments, you know, the extreme arguments about how many birds are killed and how much of this and how much water is used, and, you know, doing a comparative analysis. So we'll put that link in the follow-up email to this presentation, along with all the links that are in the chat that we've provided to get to Tom's presentation, to get to all of the great information that Tom has provided, to also provide a link for people who want to rewatch this webinar, because I've rewatched his webinars a couple of times and learned something new every time. And so I just want to thank you so much, Tom, for getting up a little extra early for us, doing this great presentation, and also staying on a little bit extra late. We really appreciate it. And the kudos in the chat are off the charts. So I hope you've seen some of them.
I really appreciate that. Thank you so much. And just out of curiosity, how many people did we have on the call today?
So I think we had 23,
Okay.
and then we have 50 that were signed up. So
Okay.
Total that were signed up. So they're all going to get the link. And then we're also going to be sharing the link to our Voices Coalition listserv, which actually has on the order of 500, 600 activists around the nation, all working on fracked gas infrastructure battles and increasingly working on false climate solutions as well. So.
Very good. Thank you, Maya, and thanks everyone for the opportunity to share this with you today.
Great. Thanks, Tom. Have a great day. Thanks everybody for joining.